So welcome again, everybody. So let me first like to inform you that this meeting is organized by on behalf of the Indian Association of the Gravitational Relativity and Gravitation, IAGRG, and with the help of Indian Institute of Technology Gandhinagar and Indian Institute of Technology Madras and Indian Association for the Cultivation of Science, Kolkata. And this meeting is dedicated to the memory of Professor Thanu Padmanabhan. All of you knows about Paddy. We are very happy and we are grateful to all the speakers who have agreed to join the meeting and agreed to contribute to that meeting. We hope for a very, very interesting seminars. All the speakers are world leading experts on related to gravitational physics. So before we start the scientific program, I will request my colleague, Professor Shubhanta Chakrabarty from Cultivation of Science, Kolkata, to share a few words about Paddy and his science. Shubhanta.
Yeah, thank you very much, Professor Sharkar, and welcome all the participants, all the colleagues to this one-day meeting on aspects of emergent gravity. And it's a really sad thing because tomorrow is the birthday, it will be the 65th birthday of Professor T. Padmanabhan. So we thought that we would arrange it on the eve of his birthday to commemorate his sudden demise. So last year on 17th September, we received this news and it sort of perturbed all of us. And this is not like the black hole perturbation which dies every week time. This is going to stay with all of us. And all of us, all the students, colleagues, and friends, all of us who knew him very well, and all the students, of course, who have greatly benefited from the books and lectures of Paddy. We were all saddened by this demise. And this has both personal as well as scientific reasons. Personally, we had many interactions with him, and in particular, he became a family member of myself because he used to call me almost every day to discuss various physics issues, issues related to computer, software, and many, many things in life. So, I just still could not believe that he is not with all of us. And his science requires no further mention. All of us knew he was a great scientist. But the point that I would like to emphasize is that he always told us that teaching is also very important. So teaching and research for him are two contemporary things. They go hand in hand. And this should be evident from the number of textbooks he has written, number of video lectures he has given, and it's innumerable. For example, today when I teach some student general relativity here or at some other institutes in India and also in abroad, many of them have learned their basics of GR from the lectures by Thanu Padmanabhan on YouTube and also by going through his book. And both of which are known for the innovative style that Paddy always had. He wanted to think in a different way. He wanted to express things in a different way. And that leads to all these areas of physics that we had worked on. So he started his career on quantum cosmology, for example. Then he moved on to cosmology, astrophysics, and various observation-related aspects. But once he has tasted the quantum gravity, he again returned back to it. And for the last 10, 15 years, he continued working on his idea that gravity is not a fundamental force, but it's possibly emerging from some underlying microscopic degrees of freedom. So there are several unfinished works, several unfinished ideas, and we being the students will try to finish as much as possible. But of course, without him, they would still in some sense remain incomplete. And his books require no further mention. So many textbooks on astrophysics, on gravitation, and in particular, his book on sleeping beauties in theoretical physics is a gem because there are so many anecdotes and so many small problems where the breadth and depth of theoretical physics can be appreciated. Recently, he also wrote a book on the history of physics with Vasanti Padmanabhan, his wife. And that was also a very interesting and intriguing book. He was in the process of creating about a 4-volume book on undergraduate physics, much like in the line of Feynman's lectures. So, but unfortunately, that did not happen. So, without any further delay and with due respect to Professor Padmanabhan or to Paddy, and I hand it over to Professor Sudipto Sarkar to start the next talk by Professor Jacobson. So I hope this conference would be a success and it would be a tribute to our beloved Paddy. So thank you all for being here, and thanks to all the speakers once again. So thank you very much. I wish it a grand success.
Thank you, Shomanta. So we welcome Professor Theodore A. Jacobson, Ted Jacobson from Maryland University, USA. I don't know, Ted, are you in Maryland or you are in Stanford? Yep. Oh, you're in Maryland.
Maryland.
Okay. So
great to see you.
Thank you. Thank you. So as always, we are very grateful for Ted for agreeing to give a seminar at this conference or meeting. So before we start, I mean, as a formality, let me introduce Professor Jacobson. I mean, Professor Jacobson is a professor at the University of Maryland, USA. And all of you knows Professor Jacobson, who is world leading expert of anything related to gravity and also quantum physics. He has been educating us on the physics of black holes, general relativity over several years, both from research point of view, as well as from the teaching and pedagogical point of view. We are all have learned our general relativity, quantum field theory in curved spacetime, and also black hole thermodynamics from a remarkable work by Professor Jacobson. And also Professor Jacobson particularly shares expertise in various ideas related to the thermodynamics, gravity, and quantum mechanics. So therefore, he is probably the most suitable person to talk about anything related to emergent gravity at this meeting. Again, I will now request Professor Jacobson to start the seminar. Thank you.
Thank you very much, Sudipta. I guess I should share my screen to start.
Sure.
I want to begin with something about Paddy. So I never, I met Paddy a few times and I didn't know him very well personally at all. Just we ran into each other at a few meetings. But I think the first time I actually became aware of him was when I would get these newsletters. I don't know how you pronounce this, Kaggle. They got sent to me in the mail at Maryland on paper. And I would peruse them just out of curiosity. And something I always really liked in them was this thing for the younger minds that was written by Paddy, actually, which is every issue had some kind of a puzzle, a physics question, and then it had the answer to the previous one. I guess you all, probably most of you all know about this. This particular one that I found, so I found the archive of these with the help of Sudipta. You've just added some cold milk to hot coffee and find it still too hot to drink. If you wish to drink the coffee quickly, what's the best strategy? Add more milk and then wait for some time? Or wait for some time and then add milk? I love this question. I love all of his questions. And I was thinking it would be really nice if somebody put these together into a book. The solution of the previous problem involves what kind of potentials have the property that the period of an oscillation is independent of the amplitude. Paddy was really creative, incredibly creative guy, and clever and prolific in his scientific output. So just a great, inspiring scientist who gave a lot of himself to the world. Now, in terms of my talk, I won't really be talking about emergent gravity, I'm afraid. I think emergent gravity is interesting, but I wanted to talk about something that I've been working on more recently. Definitely relates to thermodynamics of horizons, at least. But it's not so much focusing on the possibility of gravity being emergent. So the title is Thermodynamic Ensembles with Cosmological Horizons. this is all about work I've been doing with PhD student Batul Bani Hashemi, who I think is here participating, listening, and if I get stuck, she can help me out. So here's de Sitter as an old man. There's the static patch coordinate expression of the de Sitter metric, and there's a picture of the global de Sitter space in 2 dimensions and the static patch in it. Oh, I should have asked, can you see my cursor moving around? I don't hear you.
Yes.
Thank you. So de Sitter was not always an old man. Here he is as a dapper young man. Whoops. He was also an observational astronomer. So there he is next to a telescope. So he's definitely coming into this originally through astronomy. Now, the question I want to focus on is about de Sitter horizons and how they relate to black hole horizons and black hole thermodynamics. And this goes back to this classic paper of Gibbons and Hawking from 1977, where they, shortly after Hawking discovered the Hawking effect, they pursued the analogy between cosmological horizons and black hole horizons. And in there, they derived a first law, like a first law of horizon thermodynamics, referring to the cosmological horizon. So this is like an inside-out black hole. This red circle is the horizon. There's de Sitter looking at it with his telescope, and it's surrounding him. And he finds it has a temperature determined by the 1 over the de Sitter length. That's what kappa is. And of course, an H bar, just like the Hawking temperature, but with this value of kappa. And an entropy, just like the Bekenstein-Hawking entropy, but now of the area of the de Sitter horizon of the static patch. So that's, moreover, they showed that when the patch is perturbed, a Clausius relation or first law of thermodynamics holds, and also a generalized second law. So here's from their paper, the first law of Kerr-de Sitter space-time. The picture is for just Schwarzschild de Sitter because it's not so easy to draw a single Penrose diagram for the Kerr case. But they're focusing on a region between 2 horizons. So this singularity inside the black hole, this is future infinity in the de Sitter region. And over here is the cosmological horizon. And over here is the black hole horizon. And they're looking at the region inside there, inside the red square, labeled 1, and variations of the matter and geometry inside there satisfy this first law of event horizons, which says that if you take the killing vector K of the background de Sitter, Kerr-de Sitter spacetime, this is actually the killing vector that generates the cosmological horizon. Then the variation of the matter killing energy is related to the variation of the area of the cosmological horizon times its surface gravity, the black hole horizon times its surface gravity, and minus the angular velocity of the black hole times the change of angular momentum. What I want to focus on is just the case where there's no black hole. So it's just the de Sitter static patch. Then all the terms in this, the second and third terms on the right-hand side go away. And you just get this simple relation between the killing energy of matter change inside this causal patch and the change of the area of the event horizon, or the cosmological horizon. Now, something is strange in this formula, which is there's a minus sign. And it's strange because what it says is if you add positive killing energy to the patch, instead of the entropy going up, the entropy goes down. Now, that happens when you have a system at negative temperature. You add energy and the entropy goes down. So this is a very strange thing. Now, a system can only have negative temperature if it has a bounded spectrum of energy. Otherwise, the partition function wouldn't converge. It couldn't be in equilibrium. But Clem and Van Zo back in 2004 argued that in the de Sitter static patch does seem sort of suitable for a system that does have an upper bound to energy. And so they proposed that the reason for this minus sign is that really you should think of this patch as having negative temperature. And other people had other interpretations of this sign, which I found inferior to their interpretation. In fact, Manis Visser and I think we're probably the only people that took Clem and Van Zo seriously. I'm not sure Clem and Van Zo even take themselves seriously anymore, but it did seem like a reasonable proposal. On the other hand, how do you check like whether it really makes sense? What that question really means is, could you find the quantum statistical ensemble that describes this negative temperature patch, work out its partition function and derive meaningful, consistent thermodynamic results. So that kind of got me interested in trying to understand de Sitter thermodynamics from the point of view of a well-defined thermodynamic ensemble. Maybe I should just point out, I was going to just say here, why this result of negative temperature isn't like completely inconsistent with the first law. So if you think about what this change of killing energy would correspond to in terms of the entropy of matter, it's going to be the positive Gibbs-Hawking temperature times the change of the matter entropy. That's just the usual Clausius relation or first law of entanglement or something. On the other hand, the right-hand side is minus the Gibbs-Hawking temperature times the change of the horizon entropy. Now, since the left-hand side is minus the right-hand side, the sum of the two entropy changes, which is actually the generalized entropy change, is 0. So actually, this minus sign is exactly what you need for the statistical interpretation of this equation to be that the generalized entropy in the static patch is stationary upon variation, which is consistent with the idea that it would be maximal to begin with. I think that's a solid interpretation, but it doesn't necessarily confirm or counter the idea that the temperature is negative. It just shows this sign is consistent with a kind of equilibrium condition on the generalized entropy. Well, that's not my main point here. I just thought that's an interesting point, so I wanted to mention it. Oops. So this is what I mentioned a second ago. Can we clarify this question about the temperature by uplifting the thermodynamic description to a statistical description? What would be the quantum statistical ensemble underlying thermodynamics of the static patch of de Sitter space? Well, Gibbons and Hawking, in a paper that followed the previous one in the same issue of Physical Review D, although they submitted it 7 months later, they attempted that. Actually, most of the paper is about black holes thermodynamics described by partition functions, but in there they also address the de Sitter case. And so what they do in the paper is they formulate the grand canonical partition function at a given temperature, angular velocity, and electric potential. So for charged rotating black holes, as a path integral over spacetimes with a time period 1 over the temperature. And they approximate it by saddle point on a deformed complex integration contour. I don't want to review that. That's probably pretty well known, but the thing I want to focus on is right at the end, they consider de Sitter space, and they say since it's a closed space, we should set the mass, angular momentum, and charge to 0. And then they just interpret the logarithm of their partition function as just the area, just the entropy. So there's no free energy because the energy quantity and the chemical potentials are just zero. Everything is zero except the entropy. And they did this calculation just at the saddle point. They were talking about solutions. They used the SMAR formula to evaluate things. But I found this completely baffling because it's not clear what the corresponding path integral is. If only discussing the saddle point doesn't tell you what the path integral is. So what's the meaning of that partition function? And what is the ensemble? How is the temperature fixed? You know, if you have a boundary at infinity, you can specify the time period, which specifies the inverse temperature. But when you have a closed space with no boundary, there is no place to specify the period. So the temperature isn't specified, and yet they're getting de Sitter space, which has a particular temperature. So I just found this unsatisfactory and wanted to pursue it in a different way that made more sense. And this is where the project with Batul started. We decided to adopt the Jim York's idea that to make sense of this kind of thing, including the black hole case, you should introduce a boundary, a finite boundary, to define either the canonical or microcanonical ensemble. York originally introduced this idea in 1986. Then he worked out with Bernard Whiting in 1988, the example of a black hole in a box, like inside a bounded boundary where the temperature and metric on the boundary were specified. They worked out a path integral representation. And then a few years later with David Brown, Jim York worked out a kind of a microcanonical version of that, where they calculated by a path integral the density of states. So this is just a conceptual outline here, both of what's going on in these calculations and also partly what's going to go on in the rest of this talk. So one works out a path integral representation for either the partition function or the density of states. In this talk, I'm only going to discuss partition function for lack of time. Then this starts out as a Lorentzian path integral, but it gets deformed into a Euclidean one by a contour deformation. Now we're going to, and this is what Whiting and York did originally, a restrict to spherical symmetry. Choose a spherical boundary and then hope that the spherical configurations are representative enough to get reasonable or meaningful answers. Impose the initial value constraints for reasons I'll explain later. Identify the relevant paths. These include both black hole and cosmological horizons for the same boundary. I'll show you a picture in a moment that makes that clear. Then, of course, one wants to, you can't calculate the path integral, but you can estimate it by a very crude zero loop saddle point approximation, find entropy, find the thermodynamic phase diagram, and examine the stability of the phases in the canonical ensemble. That's what I'll describe. And finally, come back to this question about, okay, what about negative temperature? And what is this Gibbs-Hawking path integral? You know, how did they get the entropy of de Sitter space? Where did they specify the temperature? What's going on? So that's the big picture. I think the next thing is just some diagrams to indicate, visually what we're talking about here. So the ensemble is defined by conditions on a boundary here. This dashed circle represents a two-sphere of a given radius r. And the temperature is specified by the time period beta. And in this case, there's a configuration where the system is inside this boundary, so to speak, which really means it's smaller area spheres. And it goes all the way to a central point, and it really just represents a chunk of de Sitter space inside the static patch. The horizon of the patch is outside here. It lies outside the boundary, outside the system in this case. So we're not necessarily thinking of this as embedded in de Sitter space. It's like we just define a thermodynamic system by this boundary and fill it in with gravity, with a gravitational field. And that's what you get. But it's not the only thing you can get, because you could also fill it in with a black hole. Wait, this is the cosmological case. You could also fill it out. Instead of the system being the region in between the boundary and the center, it could be the region between the boundary and the cosmological horizon. So you'll see as we go on, once we formulate the path, the partition function and approximate it, look at the stationary points, that these pictures are representing stationary points of this partition function where we can approximate it. So here, again, the geometry between the boundary and the horizon
I'll let him go.
could be influenced by, I mean, it could be a Schwarzschild de Sitter solution, which would have had a black hole inside here. But again, just like before, that's not part of the system. The system is shaded in gray here. And finally, it could be the other way around. We could have a black hole inside the boundary. And we'll see that both small and large black holes play a role. So getting to more specifics, how do we define the partition function? It's, as usual definition, is trace e to the minus beta times the Hamiltonian. For gravity, the Hamiltonian is a linear combination of lapse and shift multipliers times the constraints integrated over the spatial surface plus a boundary term. So the standard story is we go from this trace to a path integral by inserting complete sets of states. We do a time slicing of this beta time, introduce complete sets of states in the Hilbert space to turn this into a path integral of paths through the reduced phase space. I say reduced because it should be, physical states that we're inserting complete sets of actual states that span the Hilbert space. Then we can represent the constraints, this vanishing of these h mu, which reduce us to the physical phase space, by delta function, which can be expressed as a functional Fourier integral, thereby introducing integral over lapse and shift into this path integral. Then the momenta can be integrated out to get it to look like just a configuration integral over the 3 metric and the lapse and the shift. And then the integration contour of the lapse and shift can be deformed, presumably to some extent, and hopefully enough so that the contours go through the stationary point of the action, of the exponent, where the partition function would pick up its dominant contribution. At that point, the lapse and shift, which started out real, are imaginary. So the contour has to at least go through those imaginary values. This yields what people normally just call the Euclidean path integral representation of the partition function, which is an integral over Euclidean metrics e to the minus the Euclidean action, which is written here. This is L is the cosmological length scale of the de Sitter space that we're fixing in everything we're doing. It's related to cosmological constant this way. We're working in 4 dimensions all the time, and we're just doing pure gravity, no higher derivative terms, on the grounds that we're looking at low energy effective physics that should be insensitive to the ultraviolet completion. At least that's the hope. And we're using Planck units. So one comment, you see these red scare quotes over this Euclidean path integral expression for Z. That's important because this contour deformation is really hiding something. You can't really go completely Euclidean on this contour. If you did, you would wind up with a path integral that had various problems. Namely, there's a conformal mode that can make the action unbounded below. And there's also, it looks like the integral doesn't actually impose the constraints h mu vanishing that we originally had to impose in order to be sitting in the physical phase space. So presumably, this deformation is okay for picking up a contribution at the saddle point. But if you're really going to implement the constraints, the rest of the contour integral is somehow important. And you don't see that if you just go to the saddle point, because then you're just solving the field equations anyway. So this will be a very important point. Okay, so then specifically, how are we going to set up our boundary conditions? We're going to take, like I mentioned, a two-sphere boundary of a particular area radius, and then the time circle will have a particular circumference. And we're imposing, therefore, Dirichlet boundary conditions on the boundary of this four-manifold. It's a three-dimensional boundary of topology S2 cross S1 of our four-manifold. We're going to set the shift vector to 0, so the boundary is not rotating or anything. And the lapse is fixed, so we get the correct period. Okay, and this Dirichlet is in red because actually there's a worry that general relativity in a finite domain with a boundary on which Dirichlet conditions are imposed may not really define a well-defined Hamiltonian system. There's been some recent work on that. I can't go into it now, but I'll just say it's a very interesting and important looking issue, and we hope to understand more about it later. But for now, we're just going to assume it's okay. It certainly was assumed for many years previous and much work previously that it was perfectly fine, but it might not be fine. So we have a spherical boundary by assumption. We can always assume that, but now we're going to assume that the relevant stationary points of the action are also spherical on account of that. And if they are, then the Birkhoff theorem tells us exactly what those stationary points are. They can only be the Schwarzschild de Sitter solutions. Since we fixed the cosmological constant, that means the only free parameter is the mass in the Schwarzschild de Sitter solution. This is a Birkhoff theorem generalized to Schwarzschild de Sitter. It was proved by Kristen Schleich and Don Witt. And it also generalizes to the Euclidean signature, which we'll need. So we're restricting then to spherically symmetric metrics. Here's a line element. This is just the unit two sphere area. Y is a radial coordinate. This point is arbitrary. So the function R of Y gives us the radius of the two spheres. Then we might need some metric coefficient in front of dy squared and dt squared. So we've partially fixed the gauge here in order to have no cross terms between tau and y. Well, and also the spheres. And our convention is that y is 0 at this boundary. So capital R is just the value of little r at 0. And beta, the period, is 2 pi times the square root of the coefficient of d tau squared. Okay. Now, crucial thing is the last point here. Because of what I was saying about the Euclidean path integral not actually imposing the constraints necessarily, we're just going to do it by hand. And this is really what was done by Whiting and York originally. And I think that's because they realized what I said, which is that otherwise the constraints are not imposed, and otherwise, therefore, you're not even in the physical phase space. So basically, our first task would be to take metrics of this form and see what the constraints say about them. And that will reduce us to the configurations that occur on the paths in our path integral. We have to say what we're doing for space because we just had the boundary here. So we're going to assume no topology change as time goes on. So fixed spatial topology. Basically, the idea behind that is that, well, first of all, if topology was changing, it wouldn't be described by this general relativity. Probably we'd need the UV completion of the theory. It's also not clear that the Hilbert space is even constant in time if the topology changes. So the whole notion of a partition function that was a trace over this stationary Hilbert space might not make sense. So in any case, we're just assuming constant spatial topology. So each spatial slice, each constant tau slice, is foliated by two spheres. The boundary is the last one. The inner end, well, there are various possibilities. The sphere could just close off to a point, and that would be like that chunk of de Sitter space. At the end, if it could be antipodally identified and make a projective plane, RP2, or it could remain finite like it does at a horizon, and then the time circle would shrink to zero size there and give us a smooth four manifold. So these are the topologies of the four manifolds that those three cases correspond to. In the first case, we have a 3-ball just across a circle. Second case, we have this, once we projectively identified the sphere at the end, we get an RP3 minus a point, so-called RP3 geon across a circle. Or in the horizon case, that's the most familiar, we just get an S2 across a two disk. So the thermal time circle is the boundary of this two disk at the boundary of the system, and it just comes in and closes off to a point at the horizon. Here are the constraints. They're just the tau tau and tau y components of Einstein's equation. And you don't need to look at the details, but I'll just point out that if r prime, see r is this function of y that gives us the area of the spheres. If r prime is 0, then the second equation is automatically satisfied. And the first equation, almost every term just vanishes, except the 1, which is divided by r squared, and 3 over L squared. So that case has a fixed radius. All the spheres have the same radius, and that radius has to agree with L over the square root of 3. And that actually corresponds to a Nari solution, not a de Sitter solution. It's an interesting special case, but it is very special, and I'm going to basically not say much about it here, just for it to save time. So if r prime is not 0, then from the second equation, we infer that v dot must vanish, which means this function v doesn't depend on tau, which means we can redefine the y coordinates so that v is 1. And that just is a simpler gauge. And then the first equation reduces to a simple first order equation with an integration constant m. It's not obvious from looking at it, but you can show that it reduces to this equation. So then r prime is just, r is just determined by integration of this expression for some m. F of r is our definition of this function, and you probably recognize this as the function that appears in the Schwarzschild-de Sitter line element. And when it vanishes is where the horizons are. So this is where 2m is equal to the horizon radius times 1 minus RH squared over L squared. And since this is a cubic equation, there's more than one solution. One of them is the black hole horizon, one is the cosmological horizon, and one is negative value of r. That doesn't make sense. I think it's negative, or is it imaginary? It's negative. U remains undetermined by the constraint, except that if you do have a horizon, it must vanish there, it turns out, for regularity of the manifold. And that vanishing is, yeah, the horizon. The time circle goes to 0 circumference at the horizon. So to get an idea of what the solutions to this equation look like, we can plot this function f of r. Since it's equal to r prime squared, it must be positive if we have a real solution for r prime. And if we don't have a real solution for r prime, we don't have a real solution for r, and we don't have a real Riemannian metric. So we're only interested in the region of r where f of r is positive. So here's a plot of f of r for different values of m. So first of all, if let's say m is too large, f of r is just negative everywhere, and there's just no real solution. There's a critical value of m, which just comes tangent to the 0 line, and that's the fixed value of r that I mentioned. That's that Narii case. There's my cursor right there. Then if m is smaller than that, we then have a region between two roots where f is positive. So there's a real solution for r prime there, and you can integrate this equation and get r. Let me just, before I talk about the details of that solution, just keep going. So the mass can decrease even more until it's 0. That would be just plain old de Sitter space. And in that case, the curve f of r goes to 1 rather than crossing the axis again, and rather than blowing up. If m is negative, it blows up as positively as r goes to 0. We take the viewpoint that the negative case is probably not physically interesting, but I'll come back to that. So now, where do we place the system boundary? It's at some value of r. Here it's shown in a red line. So for example, if we're at the 0 mass case and the boundary is here, then there are two possibilities. The system could be the solution at smaller radius going all the way to 0. And that would be the ball-shaped subspace of the static patch. Or the system could be the exterior and end at the cosmological horizon here where r equals L. But for every value of m that's larger than that, some positive mass, then the system boundary has to lie somewhere in between the two horizons. And then the system would consist of either the black hole side or the cosmological side. But both of those configurations are in the same system because the system has been defined just by the intrinsic geometry of the boundary and the temperature. And that data doesn't determine whether we consider the system to be the black hole side, which we call B for black hole, or actually I think originally Gibbons and Hawking called it B, or the cosmological side, RC, with a horizon radius RC. So now what do these geometries look like when you integrate this equation to get R as a function of Y? Well, we know from Birkhoff's theorem, these are spherical solutions. These are initial data sets within a spherical solution. So it should correspond to a static slice of Schwarzschild de Sitter. And here's that picture again of Schwarzschild de Sitter. And here's a static slice through it. So that solution can describe some region on this orange line coming through here. For example, if it's right over here where my cursor is, it could describe the region between a boundary here and a black hole horizon there, or boundary here, system boundary here, and the cosmological horizon. But that's not all it could do, because this orange slice could just keep going through the black hole horizon out to a cosmological horizon. And then it could keep going again and so forth. So those are solutions to that equation I just showed, this equation here. You can integrate it. The coordinate y would just keep going. And so that means that there are solutions that look like this chain of bubbles. Here's the system boundary, R, and the first black hole horizon on the left and the first cosmological horizon on the right. But you could just, instead of closing off the space at a black hole horizon with 0 lapse function, so closing off the time circle, you could just keep going. In fact, an infinite number of times, any indeterminate number of oscillations. Now, at each place where r prime is 0, so at each neck or each waist, there are three possible things that could happen. Like I said, you could form a horizon there by closing off the time circle. You could antipodally identify and make an RP2, or it could just keep going through it, which we call a turning point, because it's a change in the sign of the rate of change of R. Now, which ones of these should we include? It's a fact that only the monotonic case, so only if the region between capital R and RB or capital R and RC can be embedded in a four-dimensional Euclidean solution. Because if you look at the field equations, the Einstein field equations, they actually imply that anytime R prime goes to 0, U, this lapse function in the metric, or the coefficient of d tau squared in the metric, it must vanish there if you have a regular solution. So we were confused and worried about this because you have an infinite number of these configurations, and they all actually end up having the same action. So it would be really disturbing if they all contributed. But the fact that they can't be embedded in a Euclidean solution suggests to us that actually they're kind of artifacts of a bad contour deformation argument in the path integral. In other words, we don't have really control over that contour deformation that led us to this quasi-Euclidean path integral. If we just take it naively seriously, we have all these configurations. But if we include ones that can't be embedded in a solution, then in a sense, they're not really bona fide initial data sets, which is a phase space point was supposed to be an initial data set in the Lorentzian signature. And we would be kind of losing contact with that interpretation of these spatial geometries as initial data sets if we included ones that couldn't even be embedded in a Euclidean solution. So for the purpose of our project, we adopted the hypothesis that only embeddable data are relevant to the path integral. Therefore, from henceforth, I will not talk about the RP2 or these oscillating solutions. But it's interesting that they're there. Okay, let's see. So now we need to get quantitative about what is the action of these solutions, comparing the action of different ones. Well, they're solutions to the constraints. What is the action for different paths in the path integral, and which ones dominate, to find out what the thermodynamic phases are and thermodynamic quantities. So here's what the action evaluates to. It's independent of this lapse function U, except for its value at the boundary, because that determines the temperature. And it's an integral of extrinsic curvature of the boundary times the area element of the boundary minus the area of a horizon, if there is a horizon, divided by 4. And this can actually be interpreted just as beta, the inverse temperature, times the Brown-York energy, quasi-local energy at the boundary, minus the entropy. So it's just like beta times a Helmholtz free energy, where the energy term, the role is played by the Brown-York energy, and the entropy term is the Bekenstein-Hawking entropy of the horizon. And this expression can just be evaluated, maybe I should, yeah, and it can be evaluated in closed form like this, because even though we didn't write the integral for R in closed form, we only have to evaluate it at the boundary in the action. And at the boundary, it's just determined by the square root of F evaluated at the boundary. So we get this completely explicit formula. So just look at this for a second. Remember, the ensemble is defined by a boundary sphere radius and a temperature, which is given by the time period. And then the only freedom we have, given that we satisfied the constraints and we restricted to spherical symmetry, is just this one parameter M, which is the parameter in that function F, which has the interpretation of the mass parameter in the Schwarzschild-de Sitter line element. So as I mentioned, this includes, well, it's got a plus and minus sign. That's because the sign of the extrinsic curvature could be plus or minus, corresponding to whether the area is increasing or decreasing as you move away from the boundary, which corresponds to whether we're talking about a cosmological horizon or a black hole horizon type configuration. And they coexist in the ensemble, as I said before. Even if they coexist, though, that doesn't necessarily mean that transitions between them are possible. And we thought about this a lot and are pretty sure that transitions are not possible because we couldn't find any path through phase space that would connect them, any continuous path through phase space that would connect them. You know, quantum mechanically, you think about tunneling is the first thing that comes to mind. Like if you have two configurations in a system, generally one could tunnel into the other somehow quantum mechanically. But those configurations are related by a path through the classical phase space, at least in the path integral. Whereas here they're not, as far as we can tell. So we took the point of view most likely that we end up with actually separate, sort of effectively separate systems on the C or B side, but I'll point to what happens if you don't assume that. By the way, if anybody has questions, please pipe up. It would be good to address them. And I should also check on time here, shouldn't I? Sujipta, can you tell me how much time I have left?
About 15 minutes.
Okay, 15, that's probably good. Okay, so there's the action. Now, at a stationary point, which means a place where the derivative of I with respect to m is 0, then m is determined as a function of beta and r. And since m also determines the horizon radius, that's determined up to some discrete choices. And the relation between beta and the horizon radius is given by this explicit formula. I'm not sure I needed to write that because I'm not going to use that, but conceptually it's important that at a stationary point, a particular horizon radius gets chosen by the stationary condition. It turns out these solutions, even though we're reduced down to spherical symmetry, and we're only checking stationarity with respect to m variations, you know, the symmetry is so strong that they're really stationary points with respect to all variations. So they are four-dimensional solutions. And this is, again, the pictures I showed you earlier, but now you know more what lies behind them. So we call this thermal de Sitter, where the system is just a patch, a ball inside the static patch. We don't call it de Sitter because the period of this is not necessarily the right period for this to be actually embeddable globally in de Sitter space. You know, the temperature is set at the boundary here, but that might not be the right temperature to match a non-singular cosmological horizon here. So it could actually be colder than de Sitter space or hotter than de Sitter space. So we call it thermal de Sitter. Then here's the cosmological case, which has, again, topology of D2 disk, 2 disk times the sphere. And it could have a black hole, quote unquote, inside. That's really outside the system because the system is everything between the boundary and the horizon here. But this is just a way to think about what the mass parameter is doing to the geometry in the system. Now, if we really take that point of view seriously, we might allow negative masses in here because even though they're singular inside, well, they're not in the system. But if we allow negative masses, the thermodynamics of the horizon becomes pathological for a reason I'll show you. And it doesn't really make much sense, we figured, to include negative mass solutions, particularly if you try to imagine that whatever is setting the temperature on the system boundary is some physical system. That physical system couldn't have a negative mass. And finally, we have black holes, which I described before. So we want to approximate the action by this zero loop or saddle point approximation, sorry, the partition function by the approximation, namely just evaluating the integrand at the action I star, which is the minimum Euclidean action. And so to be minimum, it should be stationary. If it's stationary, it's not necessarily minimum. So we should check that it's actually a local minimum of the action, if it's going to be a good approximation to Z. And in our formalism, because we only have the M parameter to vary, we can just compare among the spherically symmetric geometries that satisfy the constraints. So we're basically just looking with respect to M. In principle, one should compare in the whole neighborhood, not just spherically symmetric, by expanding the action. And people did this going back to Gross, Perry, and Yaffe were the first ones to do it. And there's been several papers where people did this in various contexts. So what that means is you just expand the Einstein-Hilbert action to quadratic order, and you see whether or not there are any metric perturbations that can make the action even lower than the one at your, what you hope is the local minimum. So we can't actually check that because we've reduced to spherical symmetry. But in the cases where people have checked it, it's never revealed any negative, any so-called negative mode that decreases the action that wasn't already evident from just varying the mass parameter for the case of spherically symmetric configurations. So we sort of take the point of view that probably it's enough if we have a local minimum with respect to the mass parameter. So here's a plot of the action and stationary points as a function of the horizon radius. Remember, that's determined by the mass, so it's, you can think of it also as a function of the mass parameter. Here's the action, and there are kind of two branches. So each curve represents one temperature, and the left-hand side is the black hole branch, and the right-hand side is the cosmological horizon branch. Yes?
Ted, can you hear me? We are still seeing your last slide. Oh, now it's fine.
Oh, there was a delay from the
Yeah.
internet, not from me. Okay. Thank you. So should I say again? Yeah, so this is a plot of the action versus the horizon radius, which is determined by the mass parameter. And each curve is for one particular temperature. And the left-hand side is for the black hole configurations, and the right-hand side is for the cosmological configurations. In the black hole case, temperature goes up like this from curve to curve, and the cosmological side, it's the opposite, it goes down. So let me describe a little bit what we're seeing here. So for the lowest temperature, let's just look at the black hole side. For low temperature, there's no stationary point at all with respect to mass. At the very left end, there is, however, the empty de Sitter space ball. That's always available as a stationary point, and it's got the lowest action. And as we increase the temperature, we reach a critical value, which is labeled by B here, which first acquires a stationary point. And then anything above that, there are actually two stationary points on the same temperature curve. One is a local maximum, and the other is a local minimum. Well, the first time these stationary points appear, the empty de Sitter is still got the lowest action on this left endpoint. This left endpoint corresponds to the horizon radius going all the way to 0, which has the same action as the empty de Sitter with no horizon. But if you raise the temperature a little bit more, then it turns out that the lowest action is this right-hand stationary point. That's a local minimum. And that was the large black hole that I mentioned. The other stationary point is a small black hole, and it's unstable. This was pretty much exactly what Whiting and York found for the case with no cosmological constant. It's modified a little bit here by the presence of lambda, but qualitatively not really. On the cosmological branch, we have stationary points always, although for sufficiently low temperature, they would only exist out here beyond where the line became dashed. That corresponds to a negative mass. If we restrict to positive masses, the first temperature we get a stationary point is this right here. And then we can keep increasing the temperature and the stationary point moves in. But notice the stationary point is always a local maximum. So the cosmological horizon system stationary point is never, its action is never a good approximation, doesn't give a good approximation to the partition function. The lowest action, if we truncate here and disallow negative mass, then we basically have endpoints. The lowest action, for example, at this cosmological temperature corresponds to this point there, which has a horizon radius equal to the de Sitter radius L. And all of these higher temperatures, the minimum action is the de Sitter radius, and it's an endpoint, it's not a stationary point. So it's actually not a solution to the field equations. Let me describe that a little bit more here, but I should keep track of time. Well, actually, this is what I just described, so I think I can skip that. Yeah. What about this endpoint of the cosmological horizon? So if we exclude negative mass, as I said, this has got the lowest action of everything, but it's not a solution. It's a solution everywhere except at the horizon, and at the horizon, there's a conical singularity. So so how should one interpret this? In our idealized system where we constrain the mass to be non-negative, and we just have these spherical solutions, and we fix the temperature at our system boundary without worrying about physically how we fixed it. This is the equilibrium configuration, and it's stable, but it has a conical singularity in the Euclidean solution, in the Euclidean geometry. So what to make of that? Well, we decided to try to think about it from a physical process viewpoint. What's happening here is that the temperature is lower than the temperature of this horizon is lower than the boundary temperature. So if there was actually radiation flowing, it would flow from hot to cold, and energy would keep flowing across this horizon, making it want to grow. And the reservoir would be losing energy because radiation is coming out of it. So if this mass parameter that we've been talking about is somehow physically tied to the energy of the reservoir, and it goes lower and lower and lower because energy is flowing across the horizon, eventually it'll get so low that the reservoir won't have any energy left in it. If that happens physically, then it can't maintain its temperature anymore. And it just sort of evaporates away completely and the system relaxes to de Sitter space. So what I'm saying is if we realize the reservoir by a physical system embedded in de Sitter space, the sensible evolution of this instability would be it would just evolve to the empty static patch of de Sitter space. I think I should zoom ahead because I don't want to miss the last couple of points. Here's a phase diagram for the black hole side, which is basically what I described in words before, so I don't need to go over it. There's some peculiarities for the phase diagram on the cosmological side, but I think I'll skip that now in favor of having time to talk about the other 2 points. Actually, let me ask again, Sudipta, how much time is left?
I think you can take a couple of minutes.
Just a couple, yeah. So I should skip this and just make the last couple of points. Yeah, the negative temperature question and recovering GibbsHawking. So we did explore the idea of just starting with a negative temperature ensemble and writing a path integral for it. What it does is it gives you a plus sign instead of a minus sign in the exponent here. Then a configuration with maximum free energy is what dominates. That's a true fact about negative temperature ensembles. And in the spherical approximation, we can find the local maximum, and we could use it to try to approximate this. And we did that and calculate the entropy, and we get a negative entropy, which is nonsense. So it must mean that we had really an incorrect approximation to Z, because if we had faithfully approximated Z, it can't have a negative entropy. And we think what went wrong is that even though in the spherical sector, we had the maximum action, there are non-spherical fluctuations that increase the action further, as was shown by Gross, Perry, and Yaffe. So we think that's the problem. And therefore that, we have no evidence that there's a well-defined negative temperature canonical ensemble. We also pursued the microcanonical picture and calculated the temperature from that. There you don't fix a temperature, you just fix an energy. And the temperature always came out positive. So none of this thermodynamic ensembles support the idea of a negative temperature ensemble. It isn't necessarily a contradiction with the argument I gave earlier, because here we have a system boundary that's time-like, and in the static patch diamond that I was talking about before, the system was really not evolving in time. It was a fixed causal diamond with an edge and a different Hamiltonian. So maybe it's consistent that that other system has a negative temperature and this one doesn't. And let me end on this question of which is what I started with. What were Gibbons and Hawking talking about when they got the entropy of de Sitter space from a path integral, when they couldn't specify the temperature on a closed manifold? So we want to recover Gibbons and Hawking by taking the limit as R goes to 0. So here's our system boundary R. And I'm picturing this in one dimension less of space-time. So it's a 3-sphere instead of a 4-sphere it's going to be. And so I've compactified space. So infinity is the boundary. All these infinities are 1 point. So this blue square is really a hemisphere of a 2-sphere. This line up here is a circle that bounds the hemisphere. And that's the horizon. And here's the system boundary. The system is, the white part is not in the system, and it's surrounded by this horizon. Now, when we make time, we extend this in the time direction, we make a thermal time circle. So we basically rotate, we rotate this entire picture around the vertical axis. And that way this circle becomes a torus. Okay, that's the original path integral. Now we're going to shrink the system boundary down till it becomes smaller and smaller down to 0 size. Two things happen then. First of all, instead of a torus, we get just a circle, a single circle. It's supposed to have temperature, circumference beta. And the energy, the Hamiltonian in the path integral goes to 0 because the area of this circle, well, it's really a 2-sphere in our case, goes to 0 as r squared, but the extrinsic curvature goes to infinity as 1 over r. So the product goes to 0 as 1 over r. So the Brown-York energy just vanishes. And the path integral that we're doing to get this partition function just becomes the integral over all 3 geometries on the 3-sphere that have inside them a circle of circumference beta. But every 3 geometry has a circle of circumference beta, right? If you start with one that's too short, you can just put some wiggles in it and make it longer. If it's too long, you can just shorten it. So it's actually no constraint at all. The constraint of having a thermal circle just disappears and you end up with just the path integral over all metrics. Well, I should say on the 4-sphere, but I'm drawing the picture for the 3-sphere. So what does that path integral mean? Well, it was the partition function of the system with this boundary and that exists outside of this horizon. So in other words, it just becomes the partition function trace of e to the minus beta times 0, so trace of the identity in the static patch. Now, trace of the identity is nothing but the dimension of the Hilbert space. And in this case, what Hilbert space? It's the Hilbert space of all states surrounded by this horizon. So it seems like the path integral over the closed 4-manifold RS4 is, in fact, a way of calculating just the dimension of the Hilbert space of the static patch. I shouldn't call it static because I'm including fluctuating geometries, but of the patch surrounded by a horizon. And in that sense, you know, Gibbons and Hawking did something perfectly correct. They just didn't completely explain why it was correct. And I should end with that. Thank you.
Thanks a lot, Ted, for this very interesting talk. So, so the floor is now open for questions. If anybody has questions, please go ahead.
Yes. Hello, Ted. Very nice to hear you again. Nice talk. Can you hear
All
me?
right, thank you. Yes, I can.
This is Partha Majumdar. I have 2 questions, basically. The first one is that the Brown-York formalism, there's no natural choice of the boundary. There seems to be a huge ambiguity. I mean, we were
That's
doing
right.
some of these questions. So I was wondering, what if you made other choices for the boundary, like Ashtaker's non-expanding or isolated horizon, or Sean Hayward's trapping horizons? That perhaps would be a much more natural way of doing things, wouldn't it? So that's my first
that seems to touch on the question of what are suitable boundary conditions to impose at this. That's really what defines the boundary, is what kind of boundary conditions are you imposing? And as I mentioned, we're not even sure that the Dirichlet ones that we're using and have been using in the past are consistent. Maybe ones that you're mentioning would be better in that regard.
Yeah, the boundary conditions there seem to be very much natural, much more natural, because you don't have this ambiguity associated with an arbitrarily chosen system boundary. Well, I do have.
Well, I think you would still have some, you know, you'd have to choose the size, the intrinsic geometry, wouldn't you, of a slice of the boundary?
Yes, but you have a boundary already. You have an inner boundary in the cosmological case, the cosmological boundary, right? The cosmological horizon. That could serve as a boundary. I mean, you could even take a killing horizon made out of that horizon, couldn't you? And then do the path integral based on that.
Yeah, I don't know. Maybe you could. I really don't know. I haven't seen anybody try that, but you could.
Yeah, that would be fun to try, I'm sure. The other question I have is regarding, well, this is the question that has come up recently, regarding this restriction of the contour deformation to Euclidean contours. If you go beyond that, as people have been advertising, you know, Neil Turok and Jean-Luc Lehner, and also Witten and others, you could have other subtle points where you'll have instabilities which are not immediately obvious from the classical solutions. So is that something that you wonder about? Or?
Yeah, well, I wonder, but I take the most naive viewpoint in what we did here. I mean, yeah, the whole question about how to make sense of the gravitational path integral in terms of what the contour is and where the contributions really come from is something I personally have no mastery over at all. We just did the most naive
do I,
thing.
but I just heard some talks recently, and you know, I saw Witten's paper, and it seemed very intriguing that people are considering this option, because what Neil Turok and Lehner and others showed was that the no boundary proposal had led to certain instabilities, and that I found to be very interesting.
In the case of, you mean like for a wave function of the universe?
That's right, that's right.
Right. Yeah, this thermodynamics, I would say that the reason why, so Gibbons and Hawking were, of course, the pioneers in this, and they got some physically sensible answer by doing following their noses and assuming it all works out because they got the Bekenstein-Hawking entropy.
Right.
And so it just looked right because it gave a reasonable answer in that case. But that's pretty thin evidence, but it's something.
Yeah, I think that's it's good to have another look, especially in view of things that people are trying to do now, because like you said, I mean, the Euclidean path integral has definite formulational problems, right? The action is unbounded from below and so on. So that those issues, which you perfectly well mentioned, I mean, you're aware of that. But I'm just saying that maybe the Lorentzian approach would be an alternative if it is possible to do it. Maybe hard, but it's okay. Anyway, I'll stop. Thanks very much. Thanks very much.
You.
Pramanta, you have a question.
Yeah, so Ted, you mentioned about this thermality and the temperature, capital T. So whose temperature is this? I mean, it's some quantum field which is lying in the background?
You're talking about the one that defines the ensemble we've been studying?
Yes.
Yeah, that's just imposed. We imagine that there's some physical system that's the quote reservoir that establishes that temperature. And then we just ask about the statistical mechanics, or really the thermodynamic limit of that system.
Okay, no, what I was suggesting is that in case this is done by some background quantum field living on this geometry, then should not we take them also into account while computing the path integral?
Yeah, they would be like fluctuations that we're not including, both for the metric and for other fields.
Yes.
They would be at that temperature also. So, I mean, the simplest thing you could imagine is the case where we just have the empty, thermal de Sitter. That would be like a ball that's like got the de Sitter curvature in it, but it's filled with quantum fields and some radiation, some state of radiation at that temperature.
Yes. Yeah, so that would change something, do you think, or the conclusion that saddle points, would that alter any of that?
I guess the idea is that the radiation should be generally a subleading contribution to like the total entropy, assuming there's a horizon. It's not that important.
Okay.
But we kind of invoked that radiation when we were trying to come up with a dynamical interpretation of the instability of the cosmological horizon, because to have heat flowing, quote unquote heat, from the reservoir through the horizon, you need exactly what you're saying, some fields to carry that energy.
Yeah.
So I think it's like sitting there in the background, but for certain quantities, like the entropy, it's presumably subleading.
Okay. Okay. Thank you very much.
Please.
Hi, thanks. So I have a question regarding the negative temperature, which you, the case which you mentioned, Ted. So this is very naive, but the question is, suppose I don't look at the Lorentzian path integral, but only the Euclidean one. And if I take it to be the exponential of minus negative modulus of I, would that, would that work in some way, or?
Let's see, minus the modulus of I, is that what you said?
Yes. It's just that if I define the Euclidean action and the Euclidean path integral to be like that, without really bothering about whether its Lorentzian extension does exist or not. Okay, and will that, because you saw that you had a positive sign coming up there?
Yeah, I don't know. I can't see how to motivate from first principles taking that absolute value. If you start with trace of e to the minus beta h, where beta is negative, so that's trace of e to the plus modulus of beta h, and then you represent that as a path integral, you get the expression I wrote with a plus sign times the action.
Yeah.
So I don't see how I would arrive at the expression you were describing.
No, I was just thinking as a matter of starting principle, if one posits that one take the mod there and then work it out, then what could happen?
Right. Yeah, I don't know. But I also don't know what it would correspond to and from first principles.
Yeah, that is true. That is true. Yeah. Okay, thanks. That's
Is there any other question from anybody?
Yeah, Sudipto, can I ask something?
Please,
This is
please,
Dan here.
please.
Yeah, thanks for a very nice talk. Could you just go to the slide IH versus RH plot, the
Yeah.
one that you showed? Yeah. I just wanted to understand a little bit about, yeah, this one. So here, the expression with the two signs, minus and plus, they correspond to the two branches, right? Is
Yes.
that what you mean?
Mm-hmm.
Yeah, and IH is always negative.
Not on the, see here it goes above.
Yeah.
At low enough temperature on the cosmological side, it goes above. Because this term becomes, so the cosmological side is the plus sign.
Yeah, so what would that mean? What is
And so what would it mean?
yeah.
That it becomes positive, you mean?
Yes, both signs and all that in terms of the value of IH as such.
Let's see if I can say something intelligent. Yeah, all I can say is mathematically, because beta is becoming very large at low temperature.
Yes.
It's multiplying a non-zero thing. It just keeps growing and eventually it outweighs the negative horizon entropy term. But I don't know, I can't say anything more physically interesting.
Okay. The other question I had is a general one. When you mentioned at the beginning of the talk that this is related to the idea of emergent gravity. So could you a little bit elaborate on that, since it's a meeting on?
Oh,
yeah.
Did I say it was or did I say it wasn't?
Yeah.
Yeah, I guess I just meant, I mean, I really was apologizing that it's not related, except insofar as we think that thermodynamic properties of horizons are, like a window into possibly interpretation of gravity as emergent. I mean, I guess I would have, the point in my talk that makes the closest contact with that, I would say, is when I interpreted the first law in de Sitter space as the statement that the variation of the generalized entropy is zero. So this makes contact with the idea I pursued earlier, which is that the vacuum is like an equilibrium state, and the field equations of gravity are the expression of the condition that the entropy is maximized in a causal diamond in the vacuum state. So I didn't go into that at all in this talk, but that's the closest place where those ideas connect. What's emergent about that in my mind is that, why should the vacuum be the maximum entropy state? By the way, when I say maximum entropy, I'm talking about you add both the entanglement entropy of quantum fields in a region and the horizon entropy, which is actually probably the UV correspondent of that entanglement entropy. Why should it be maximum in the vacuum? Why should the vacuum be a maximum entropy state when maximum entropy normally means equilibrium? So it's like as if the vacuum of space-time is some equilibrium state of something else. And in that sense, it's emergent from whatever it is that's in equilibrium. I'm personally a little bit at a loss to make that concept more concrete. The name emergent gravity exists in its use, but I don't really know what it means beyond what I've said.
Yeah, but this ensemble that you mentioned, so this ensemble must consist of some microscopic degrees of freedom, right? So I can think that these results of temperature and entropy which we are getting are effectively coming from this microscopic degrees which forms
That's
the
true.
ensemble.
But
So
here we were taking the very conservative, quote unquote, view that those microscopic degrees of freedom are nothing but the degrees of freedom of the gravitational field as we know it. And therefore when we implement the partition function, we're just summing over gravitational field configurations rather than trying to guess at some other structure that's underlying that.
yes, that is true. Thank you.
Great.
Yeah,
Thanks
thank
a
you.
lot,
And it's
everybody.
thanks a lot.
Thanks a lot, Shayan
Yeah.
and Sumanta. So since there is no more questions from the
Sorry, Sudipta, may I
please
ask a
go ahead.
question?
Please go ahead. Please go ahead, Isha.
Yeah, hi Ted, it was a very nice talk. Thank you. So it's a comment / a question following up on Supreet's question, suggestion, I guess. So for example, in experimental systems like spin systems or hydrodynamic vortices, where negative temperature results have been studied. So this flip in beta, if it is accompanied by a population inversion, which would then correspond to, for example, the Hamiltonian now being bounded from above, then the partition function is normalized and sort of everything works out fine. So I was wondering if in your formalism, this inversion of beta also can be naturally associated with somehow an inversion in the Euclidean action. Because if that were the case, then you would still have, so you would have the situation something like e to the minus modulus of I. So well, that's the question, if that can naturally occur in your setup.
So you think population inversion translates into taking modulus of the action?
No, so that would population inversion would correspond to also having an inversion of the Hamiltonian, which would then amount to still having a modular Hamiltonian that is bounded from below, which is,
Right.
I guess, what you need for normalization.
Yeah, all I know is that, so what the people that first suggested this, Clem and Vanzo, they were saying that if you try to put more energy inside the static patch than a certain limit, then you would have a black hole whose size was bigger than the horizon radius. So since the de Sitter length sets a particular kind of boundary size, they argued it makes sense that the Hamiltonian is bounded above. Just because it's like a compact region of a fixed size, and it would collapse into nothing, into itself, to its own black hole if you put too much energy in it. That's how they justified the idea that its Hamiltonian was bounded above. They also said, well, we know that the de Sitter, we think the de Sitter horizon has an entropy that's finite, A/4 with a finite area. And so that's like saying that the Hilbert space is somehow finite dimensional. And you hear this a lot. People think that this Hilbert space of the static patch is finite dimensional. Well, if it really is, then the Hamiltonian is automatically bounded above because there's just a finite dimension of states anyway. I think those were the ideas behind their suggestion. But in what we're doing, we have no indication or way of capturing that idea. Our Hamiltonian is not bounded above, but maybe we're talking about a different system, a different kind of Hamiltonian. Like I think the Hamiltonian that in the case of Clem and Vanzo and the causal diamond, it's the one that evolves a surface. So here's the edge of the causal diamond in space, and you can deform it toward the future in time, but keeping the edge of it fixed. And that Hamiltonian that flows within the causal diamond is a different Hamiltonian than the one we're talking about, because we have a fixed boundary that's extending in time, and it's the Brown-York Hamiltonian. So maybe a totally different viewpoint on what the dynamics is in a causal diamond would still make sense with negative temperature.
Mhm.
But I don't know.
All right, yeah, thanks. Actually, may I ask another question, a different
Please,
question?
Fine with me, if it's fine with
Uh,
Sudipta.
Please go ahead.
Okay, thank you. So when you're introducing this boundary, it looks like now you're considering bipartite systems. So it's a speculative question, and I was wondering if you have any comments on any relation to thinking of your setup as an open quantum system or not.
I don't, because for us, we wanted the boundary to delineate the end of the system. And it's open in the sense that we're specifying a temperature on it, I guess. So we have an ensemble, it's a mixed state. In that sense, it's open. I mean, but that's true about any canonical ensemble, because it's the Gibbs ensemble is a mixed state density matrix. Of course, we also considered the microcanonical case, which isn't. But so since we're only looking at equilibrium, I don't know how you would diagnose, what it would mean for it to be an open system. It's open in the sense that it's connected to a reservoir that's fixing its temperature. And, but since we're assuming it's in equilibrium, that doesn't change anything about the state over time.
Right, okay, yeah, okay, I see. So the more interesting physics could come out if you had somehow non-steady state conditions or non-equilibrium conditions. Yeah. Okay, thank you.
Thanks a lot, Esha. So from all the organizers, we like to thank Ted for this wonderful talk. And we are really happy that there are so many discussion after the talk.